Okay, so let's go through some basic transformations. The first one of these is identity. The idea of the identity matrix is it does nothing to the result. So we have some sort of 4x4 matrix. We multiply it with this 4-dimensional vector. We want to get the same 4-dimensional vector back. Okay, no problem. So we think, okay, well, we want to get x here. So the way we get x is we have 1 times x plus 0 times y, 0 times z, plus 0 times 1. That's the first row. The way we get y is we have 0 times x, 1 times y. We can kind of see a pattern here. So the way the identity works is we have 1s on the leading diagonal, and we can go through this. So we have 0 times x, 1 times y. So that's y plus 0 times z plus 0 times 1. And then for the z, we have 0 times x. So we go along this way, down this way. 0 times x plus 0 times y plus 1 times z plus 0 times 1. And then for the last element here, we have 0 times x, 0 times y, 0 times z, and 1 times 1. So we get 1 as our result. So the reason we need 1 in the last dimension is so that we can handle translations, and that's what we'll see now. Okay, so the next thing we want to do is we want to handle translation. The idea is we pick up a point, x, y, z, and we translate it by some point so that it goes to x plus a, y plus b, we'll say, and z plus c. Awesome. Okay, so we'll use the same sort of technique here, so we'll kind of build our matrix. We want our result to be x plus a, as described here. So what we'll do is we'll take 1 times x, 0 times y, 0 times z, plus a times 1. That's why that 1 is there, so that we can use matrix multiplication to include all sort of transformations, including translation. And then we'll just continue. So if we go ahead and do this matrix transformation, we have y plus b times 1, z plus c times 1, and just 1 times 1. So it's really important to note that the upper 3x3 is just the identity. The upper 3x3, usually it tracks scaling and rotation. So we can see no scaling and rotation has really been applied here. That's retained. It's just the kind of the right column is tracking translation, which we can see has been applied there. Okay. The next one we want to look at is rotation. I'm so keen to write x. Anyway, so. Alrighty. So what I'm going to do is I'm going to track, I have some basic vectors. We'll call this vector I, that is 1, 0, 0. And when we translate a point around the x-axis, that I vector isn't going to change at all. Perhaps a little more interesting is the j vector. So when we rotate this j vector around the x-axis, it kind of spins this way by an angle and maps to this image point. Now if we look here, we can see in the x-axis there's nothing there. In the y-axis, it's the hypotenuse of this hypotenuse of this right angle triangle we've got here. So that is, sorry, not hypotenuse, the adjacent side, so that's cos theta. In the z-axis, it's sine theta. And then if we look at the z-axis, we have the fundamental vector, the elementary vector k, and that will rotate back around this way. This forms a right angle triangle. So this k dash in this case has nothing in the x. Its y-axis is now pointing in the negative y-axis direction, and that is the opposite side of that triangle, so sine theta. And in the z-axis, it's pointing in the positive z, so it's and it's also the adjacent side of that triangle, which makes it cosine theta. So what we do is we say, okay, so to rotate in the x-axis around an angle of theta is to stick together the images, basically, as columns here, and that is in the x, in the y, in the z, and running out of room here, but also just that one on the end there. So again, we can see that the upper square of the matrix has just got the rotation information, and on the right hand side, the right column, is the identity column, which indicates that there is no translation occurring, it's just a rotation. Now, this is just a simple example, although it's kind of messy, so I did a good job of complicating it. If we want to find a general rotation, so let's say we have a set of Eulers, a vector which has a rotation around the x-axis, y-axis, and z-axis, then what we do is we take rotation around the z-axis by its angle, times that by the rotation around the y-axis by its angle, and times that by rotation around the x-axis by its angle. Cool. Okay, so now things start to get a little more complicated. Let's say we want to look at something, so we want to do a view transformation. So we're going to make a look-at matrix. Ideally, we want to have a position that we're looking from, a point that we're looking at, and an up vector as well. Okay, so let's say we have a camera, and the camera has kind of an up vector and a forwards vector, and we have some point over here. So the first thing we do is we subtract or translate according to the camera's position. So we subtract the camera's position from everything in the scene. This sets it up so that the camera is the center of the world, so everything kind of shifts over. And then the next step that we do is we rotate kind of inversely to the camera. So we rotate in such a way that the forwards and the up kind of align with some sort of axis. And so as we can see, the camera was looking kind of directly at this point, and that's what it's doing in the final result. The difference is just that things have kind of been spun around a little bit. So the way I found this look-at vector is I kind of looked it up online. I did a little bit of a look at myself. So I'll just write it up, and then I'll kind of explain how this lines up with what we see here. Okay, so if we look at the upper, the upper square of the matrix, as I was saying, this typically tracks rotation and translation. Sorry, rotation and scaling, not translation, specifically not. We see that we have a kind of rotation action based on the up, right, and forward vectors of the camera. So in some sense, this is doing rotation based on the camera's kind of direction. And then if we look at the right column, this is tracking the translation. We are translating in some way opposite to the eye, the camera's position. Now there is a little bit of a funky thing going on because we're taking a dot product with the camera's position, but it just is what it is. Like I said, I had a little bit of a looked up on Wikipedia. But yeah, okay, so that's a look at matrix. Okay, so let's say we've done our view transformation. So everything is all normalized and everything. The last thing we need to do is perspective. Now there are two things we need to do with perspective. The first one is perform perspective division so that things which are farther away from the camera look smaller. And the second thing we need to do is track the distance that something is from the camera in order to fill a Z buffer and have proper backface culling and all of that. So kind of what we're doing is we have a view frustum where there's a far plane and a near plane, and what will happen is this will kind of be mapped to kind of a normalized thing. So objects which are on the far plane will be squashed down, make them smaller, and that's kind of what's happening. But it's a little bit hard to see, so I'm actually going to redraw this. Okay, so let's say, for instance, that we're looking in the x-axis. It doesn't matter which axis, all axes are kind of the same here. We have, actually, that's fine. We'll call this f distance, so the far distance. And this is the near distance. And there's some point somewhere which has an x point and some distance, which is somewhere between the near distance and the far distance. Our viewer is over here. And what we want to do is we want to kind of cast through and find which sort of, what the x-dash coordinate should really be in this case. So what we have is we can do similar triangles. So we have, by similar triangles, this proportion here should be equal to this proportion here. So we have x dash over the near, that gradient there, is equal to x over z. We can then transform this, multiplying on both sides, and we get x dash is equal to that sort of situation there. And similarly, y transforms to near y divided by z, z transforms to z. So what we want to have is we want to have a matrix. We put in our input. Going to be a little tricky here. See, we have nx over z, but this sort of linear transformation, like we kind of can't do that. So what we'll do instead is we'll multiply all components. So instead of having nx on z, we want nx as our x output, and y as our y output. What is it? Z squared as our z output, and z as our kind of w output. What happens is when we pass in this sort of vector, Metal automatically does perspective division, so it divides all these components by the last element, and that's how we kind of get what we want. So what do we have? Well, for x, it's just n times x plus 0 times y, 0 times z, 0 times 1. For y, it is 0 times x, n times y, 0 times z, 0 times 1. For the fourth row, it's 0 times x, 0 times y, 1 times z, and 0 times 1. But then things get a little trickier. So what we want is we want 0, 0, and then something and something, which I'm going to call, doesn't matter. These are unknowns. And what we're going to say is that if we take all of this, so we have what? We have a times z plus b equals z squared. Okay, and what we'll do is we'll say that this equation, it can only have two solutions. So we'll just plug it in artificially and we'll say this equation is completely true at the near and far plane. So we'll have an plus b equals n squared. That's equation 1. And f, sorry, for the far plane. That's equation 2. Okay, so let's go ahead and solve this system of equations. Okay, well, I know I scared us a little bit talking about quadratic equations, but now we're solving with respect to a and b, so these are linear equations. We can simply take, I don't know, equation 1, subtract equation 2. So then that would be a times, so an minus af, which factorizes into an minus f. B take b goes away. And then we have n squared minus f squared. But that's a difference of squares, so that factorizes into n minus f times n plus f. Awesome. Then we just divide on both sides. So we've got an expression for a. Then let's take equation 1 and 2 and multiply them to get a common term, a and f, which we can then subtract. So we'll take the system of equations becomes multiply the first equation by f, and the second equation by n, and then go ahead and subtract that. So this common term cancels out. We have that, which factorizes, if we take on a factor of nf, factorizes into n minus f. So then dividing on both sides, we get b is equal to, which which comes out to negative NF. And this is kind of the foundation from which the perspective transformation comes from. So let me just write this out for completeness. So there it is. That's the basic perspective transformation. So. There's a few things to consider with metal. Two things, actually. One thing is metal is, if I can write, it's left-handed, and matrices are stored in column major form as opposed to row major. So what this means, left-handed, simply means we need to reverse the cross product. So in our math operations, if we ever try to take cross products to get orthogonal directions and stuff, we always need to either reverse the order of the cross product so that by the right-hand rule we're getting the wrong result. Okay, that's the left-hand rule. Or just apply a negative in front of a cross product, because changing like A cross B is equal to negative B cross A. Changing the order just means applying a negative, and that's the left-handed thing. By the way, left-handed rule is actually kind of makes more sense than you'd think. So let's say we have the x-axis going here, the y-axis going here, and then we apply the cross product x cross y or I cross j or something. By the right-hand rule, that would be pointing backwards at us. But let's say we want the positive z-axis to be... No. What am I thinking? X cross y always has to be pointing in the positive z-axis. So this means that if our camera is here at the center, then objects which are like we're looking at them need to have a negative z value, which is not very intuitive. So the way we reverse that is, this is the right-hand rule. By the left-hand rule, x cross y would be pointing the other way, and so with the left-hand rule, positive z values are in front of the camera, if that makes sense, and zero is at the camera, negatives is behind the camera. The other thing is we have column major, not row major, and all this means is we transpose matrices. So the way I'd make a math library is I'd make a matrix in the standard form. Then I would, anywhere I see a cross product, just apply a negative or reverse the cross product. And anywhere in my final result, always like transpose it. Anyway, so let's jump into the code and look at how we've implemented these. All right, so let's get this party started. We'll just hop over to our environment, and here we have transformations. Open up this project. Link is in the description. And first up, let's just run it, see what it looks like. Okay, excellent. So we've got the same triangle that we had in the video before. Side note, down below we have some debug info, and sometimes it just randomly throws errors. It says things like fopen failed and things. And I looked this up online, and the way we fix this situation is we go up to product and then clean build folder. And I mean, that usually gets rid of the errors. It did in my case. Okay, so I guess I'll just really super briefly step through how I've refactored this. We have our top level control, which returns an app view. Now, the reason I made an app view and a content view is that the content view has the UI kit view, there. But the thing with a UIKit view is we can't really like wrap it in modifiers the same way that we can with a SwiftUI view, which is why I have got that. I've got this separate thing here. So for instance, we can embed this within a vertical stack. Let's just see if this works. Yeah, so it is a little dodgy. I mean, we're probably not meant to do this sort of thing, but the option's there if we want. It's kind of, yeah, won't worry about that. But anyway, so we have that. What we should probably be doing is playing around with the padding and things. See that it allocated some space to write the text, but I think the padding was off a little bit, which is why it looks really, really dodgy. Oh, right. Okay. No. What's happened is this is stretching off beyond the view, and so the text was probably off to the left here. That really wasn't my point. My point is we can use this the same way we would use a traditional SwiftUI view. Okay. So back on track. So we have this situation here. We have a renderer object, a triangle mesh object. Now all the triangle mesh object does is stores the vertex buffer. And when we create it, we need to pass in a reference to the device used by our renderer because that allocates the buffer. But we also have these model classes. We have a scene, and the scene has a camera and a list of triangles. At the moment, it's just one. And each of these objects has their own functions and things. So the camera has positions and rotations and a function here to calculate its forwards, up, and right vectors. So as I said, link is in the description. So the question is, how do we take this and add linear like transformations and things? I'll just paste this in. So I made a library called Linear Algebra. It's a joke from back in uni. When we were studying maths, we had a study group. We called ourselves the Linear Algebros, but I figured it was relevant to linear algebra. So I'll just kind of step through this super quickly. We have this identity function. And this pretty much lines up with what I discussed earlier. Because remember, when we take the transpose of an identity, because it's symmetric, the transpose won't change it. If we look at translation, that does look different because it's been transposed. So usually we would have the rightmost column in standard form stores the transformation, but because we are in column major form, not row major form, we take the transpose, and it's this row here which has the translation info, and this is like the upper 3, the upper 9, which is the identity. Then if we look at the we have rotation functions here, which is kind of hard coded, no worries. And then we have the look at and perspective. So with the look at, again, it's this, take the transpose, and this is the upper 3x3, which has the rotation for the camera. And this is the column for the translation. And we just do a bit of internal work as well, just to make sure that we have got the correct forwards, up, and right vectors. That's just using cross products. Okay, and then for the perspective, it's very similar. We're just also factoring in the field of view parameter, as well as, for instance, as well as each of these components has kind of been normalized by dividing by the far minus near. Yeah, but there we have it. Okay, so let's dive in. And like I said, link is in the description. You can grab this, you can use it for your projects. That's perfectly fine. But let's have a look at how we can actually use these things. So let's go to the shaders and just prepare this. Okay, so the first thing I want to do is pass in a model transformation. Model transformations will be passed in once per object. So I'm going to make them a parameter here. So we'll go. And we're going to pass them in by kind of setting some bytes, which we'll get to in a second. But we've already set buffer number 0 here. So now we're going to set index 1 on the buffer. So what are we going to do? We're going to simply take this, multiply by this model. And we need to put a comma there. Okay, awesome. So now we can go to the renderer. And we'll go for each triangle. So again, linear algebra is kind of like a global class which has all these functions which return things. So we can simply go inside there and go create, let's rotate first. And then after rotating, we will stack on a translation. So something that I really like is if we look at the order of operations, this is a little closer to, what do you mean can't find try? Oh yeah, because I spelled it wrong. This is a little closer to the mathematical way that matrices work. They multiply on the left. It always bothered me that GLM did this like multiplying on the right thing, or at least the way it went in the C++ calls. This sits better with me. Okay, so the next thing we need to do is we need to get that to the, get it to the, what am I thinking? Shader. So we need to set vertex bytes. The first thing we need is a reference to the thing that we're sending in. We're going to send in that model matrix. And then we have the size of the thing that we're sending in. Which is essentially the stride of that data structure. It's how big is it in memory. And then the last thing we need is the index. Now we used index 0 already on the buffer, so now we're going to use index 1. Cool. All right, so let's set this up so that the triangle is doing something. If we go to render scene, by the way, render scene is a little bit of a strange name. I mean a scene which gets rendered. I don't mean a function which renders a scene, but I can't call this class a scene because scene has a special meaning within SwiftUI, within Xcode, which is a lot of fun because I set it up with the class named scene and then it complained saying that my app wasn't conforming to scene, and that was a nightmare because there's... Anyway, so where was I? So what are we doing? We're setting this. Let's just run this. So that's not great. we're seeing nothing. Looks a bit strange. Let's go rotate this around the Z. And let's set this at 0 because, oh yeah, let's simplify all of this. Okay, so the camera, we're going to put it at the origin. With around the y-axis, 90 degrees will be looking horizontal. 0 is straight up, 180 is straight down. And okay, so the camera will be at the origin looking along the positive x-axis. And if we set this up, this should work. We've got a triangle, but it's not spinning. Even if we set this to something really big, it kind of spins a little bit, which is strange, right? So yeah, it just complains if I exit the wrong way. So what we need to do, where was it? Okay, so content view has this metal kit view thing. There's a property that we need to set. It's is paused. So if is paused is true, then it will only kind of run once and then pause. We don't want that. We want it to update all the time. And there we have it. It's working. But have a look at this. Something funny happens. So there's two things. Number one, this is still set up so that Y is up and down. So we haven't really, I don't like programming that way. I think that's dodgy, at least for 3D. And then number two is if we set this to rotate around a different axis, we get some kind of horrible effects happening. See, it's only showing half the triangle and then it flips over and shows the other half. Obviously, this is really bad. And the issue is it has to do with like near and far planes because the triangle is kind of rendering actually at the eye level of the camera. So you're only going to see half of the triangle. One half is in front of the camera, one half is behind the camera. But that is really annoying. So let's just leave this for now. We're just experimenting. And now let's create the view transformation. So in order to do this, I'm going to ultimately pass in two things. I'm going to pass in a view and a projection. So because I'm passing in a view, I'm going to make a data structure for this. We'll just go with that for now. Okay, so let me go to the shaders and we're going to, in addition to this, take in a camera object, index 2 on the buffer, and camera view. Okay, cool. So now what we want to do is we want to go into not there. We want to go into this. And the camera is kind of set once each frame. So we'll say of course, because I've got a camera object, but I'm calling it the player. Okay, cool. So no worries, we have set that up. We then just send that into the shader. Index 2, okay, awesome. It's looking good. So now we can run that. And see, now we've got a problem. Because before we were setting the triangle up right kind of at the camera's eye, but we weren't kind of taking that into account. But when we run this make the view, then we subtract the camera's position, and what that essentially does is just it sets it up so the so the triangle is right on the camera. There's a few things we can do to fix that. One thing we can do is maybe rotate around a different axis. So rotating around the Y, so this should be spinning around the vertical. Kind of, it's a little, I don't know, a little funky, but that's okay. See, it's still kind of messed up. That's okay. What happens if we go around the X? Nothing good. So what we can do now is we can set the camera a little bit back from the, no, not the camera, sorry. Set the triangle a little bit back from the camera. Ah, of course, what am I thinking? What am I thinking? Okay, so before Y was up, but now Z is up. So if we go to our triangle mesh and just reverse this around, now because the view transformation takes into account the direction that the camera is actually facing, now Z is up. And that's what I was missing before. So if we run this, now this should work. See, now we're rotating around the Z axis and it's up. Now, and similarly, if I set this so that we're at an X of 0, okay, fair enough. Nudge it a little bit past the camera. Okay, cool. So now it's working. Now, where were we? Right, projection, of course. So no problem. We just go to our definitions and we're going to add projection matrix. And in our shader, also going to multiply there. Okay, cool. So we've set the camera's view. Come on. Now we're going to set its projection. Okay. Field of view is going to be 45 degrees. Aspect is just width over height, so 800 over 600 or 4/3. Near is we're not going to draw anything closer than 0.1. Far, we're not going to draw anything further than 10. And see, there's a side effect here. Earlier, we were not doing perspective division. So even though the triangle was really close to our eyes, it wasn't big, but now that's corrected for. And if we go to the scene and we push this triangle back a little bit, so we'll push it back like 5 units, then it should be smaller. There we have it. That's nice. That's cool. We can also spin the camera around, do all sorts of cool things. But yeah, we'll leave that there for now. I hope you had fun. Hope you learned some things, and I will see you in the next one. Bye.